Black holes function simultaneously as the most rigorous test beds and the clearest failure points for our current understanding of physics. On the test bed side, general relativity has been tested in black hole environments more severely than anywhere else, and it keeps passing. The shadow size of M87 Keex matches the prediction from orbital mass measurements to within a few percent. S2's orbit precesses exactly as Schwarzschild geometry predicts. LIGO waveforms match numerical relativity solutions of Einstein's equations to a level of precision that would have seemed implausible a decade before the first detection. Every time we measure a new property of a black hole and compare it to theory, general relativity wins. This is remarkable for a theory developed in 1915 in a world with no computers, no particle accelerators, no space telescopes, no means of imagining that we'd one day receive gravitational signals from events 1.3 billion light-years away. On the failure point side, the singularity exposes general relativity's incompleteness as clearly as anything in physics. The infinities the equations produce at the singularity are not computational artifacts. They're the theory's honest acknowledgement that it breaks down there. Quantum gravity, whatever it is, must take over, and we don't yet have it. The Hawking radiation calculation exposes a different incompleteness. The tension between the second law of thermodynamics, entropy increases, unitarity in quantum mechanics, information is conserved, and the prediction of general relativity that information can be lost inside black holes. These three pillars of physics cannot all be simultaneously correct without modification. Resolving the information paradox will require revising at least one of them. Beyond fundamental physics, black holes have transformed our understanding of galaxy formation and evolution. The M-sigma relation, the tight empirical correlation between black hole mass and stellar velocity dispersion in galactic bulgy holds across many orders of magnitude and was discovered in the late 1990s. It tells us that the black hole at a galaxy center and the galaxy's stellar population grew together, regulating each other. Models of galaxy formation that ignore black hole feedback produce galaxies that are far too massive and far too actively star-forming compared to what we observe. Models that include AGN feedback, the jets, the radiation, the mechanical energy deposited into surrounding gas, reproduce observed galaxy properties much more accurately. In this sense, the history of the universe as we observe it, the galaxy mass function, the cosmic star formation rate density, the size and color distribution of galaxies bears the imprint of black hole activity across cosmic time. The universe we live in is shaped, in part, by the supermassive black holes at galactic centers that have been heating, stirring, and suppressing star formation since the first galaxies assembled. The equations of general relativity do, in fact, permit wormholes. An Einstein-Rosen bridge, named for Einstein and Rosen, who described it in 1935, is a solution to Einstein's field equations that connects two separate regions of spacetime through a tunnel. In the maximally extended Kruskal-Sackeres spacetime for a non-rotating black hole, the complete solution contains not just the exterior universe and the black hole interior, but a second exterior universe connected through a bridge at the singularity. The mathematics is sound. The geometry is valid. A wormhole solution exists. The problem is physical realizability. The Einstein-Rosen bridge of a Schwarzschild black hole closes in zero proper time. Any particle entering the bridge from one side finds the bridge pinching off before it can reach the other side. This isn't a matter of going fast enough. The closure is geometric, not dynamical. Regardless of speed, no particle can traverse the classical Schwarzschild wormhole. For a wormhole to remain open long enough for a particle to traverse it, the throat must be threaded with material of negative energy density, exotic matter. Negative energy density means a stress energy tensor with negative components in the time-like direction. Material that has less energy per unit volume than the quantum vacuum. Quantum mechanics does produce negative energy densities. The Casimir effect, the measurable attractive force between two uncharged conducting plates placed very close together, arises because the quantum vacuum between the plates has lower energy than the vacuum outside, due to the suppression of certain electromagnetic modes between the plates. Negative energy density, in the Casimir sense, is real and measured. The difficulty: Casimir-type negative energies are extremely small in magnitude, spread over specific geometric configurations, and subject to quantum inequalities. Theorems that bound how large and how long-lived negative energy densities can be. The quantities required to stabilize a macroscopic traversable wormhole exceed what quantum inequalities allow by many orders of magnitude, under any mechanism currently known or plausibly conceivable. Most physicists regard macroscopic traversable wormholes as almost, certainly physically impossible, not because the equations prohibit them, but because the energy conditions required seem to be ruled out by quantum mechanics. I want to close with something beyond the physics. A black hole is the universe following its own logic past the point where human intuition can accompany it. The same equations that describe the orbit of the moon, the precession of Mercury, the bending of starlight during a solar eclipse, taken to their limit, in the presence of sufficient mass in sufficient compression, produce a region of space-time from which nothing returns. Light, matter, time itself bends toward a singularity that the equations cannot describe. There's something honest about that. Physics doesn't pretend the singularity is resolved. The equations raise their hand and say, "Here is where I stop." Something more is required. We haven't found it yet, and we're looking. The Event Horizon Telescope was an act of looking. Hundreds of scientists, coordinating telescopes on multiple continents and a polar station, physically shipping petabytes of hard drives from Antarctica to take a photograph of an object 55 million light-years away whose shadow is 42 micro-arc-seconds across. They succeeded. LIGO was an act of looking. Decades of engineering, building mirrors that don't vibrate, lasers that don't drift, seismic isolation systems that decouple a 4-kilometer interferometer from trucks on nearby roads, to detect a ripple in space-time from two black holes merging 1.3 billion years ago. They succeeded. Genzel and Gez were acts of looking, decades of tracking. Individual stars moving at 2.55% of light speed around an invisible point. 26,000 light-years from Earth to weigh a 4 million solar mass object and confirm it. Matches what general relativity predicts for a supermassive black hole. They succeeded. The universe contains objects so extreme that our best theories break down in their interiors. And we went looking for them anyway, built the tools to find them, measured their properties to 4 decimal places, photographed their shadows at micro-arc-second resolution, heard their mergers in gravitational waves across cosmological distances. The true scale of a black hole is, yes, its event horizon, from 18 kilometers for the smallest stellar objects to 393 billion kilometers for TON 618. But measured differently. The scale of a black hole is also the scale of what studying them has required from us. The theories, the instruments, the decades of work, the willingness to ask what happens where physics breaks down and then actually try to find out. The map runs out at the singularity. The territory continues, and people are going, next century will be made. That's where we end. From stellar collapse in a quarter of a second to event horizons that take light 2 weeks to cross. From a clock ticking at 10% of its distant rate just above the event horizon to a singularity where our clocks and our equations stop entirely. From the first photograph of a shadow 42 micro-arc seconds across, to gravitational waves detected at 10 or 21 fractional strain, to 100 quintillion black holes scattered across the observable universe, almost all of them invisible. This is what a black hole actually is, sized, measured, traced through its physics, in numbers that hold up. If you stayed to the end of this, thank you. That's what this channel is built for. The people who stay to the end. Drop that comment if you haven't already. Where in the world are you right now? I want to know. Subscribe if you're not already. More of this is coming. The same level of depth, the same commitment to actual understanding on the strangest and most beautiful things the universe has made. Until next time, sleep well. Black holes function simultaneously as the most rigorous test beds and the clearest failure points for our current understanding of physics. On the test bed side, general relativity has been tested in black hole environments more severely than anywhere else, and it keeps passing. The shadow size of M87T matches the prediction from orbital mass measurements to within a few percent. S2's orbit precesses exactly as Schwarzschild geometry predicts. LIGO waveforms match numerical relativity solutions of Einstein's equations to a level of precision that would have seemed implausible a decade before the first detection. Every time we measure a new property of a black hole and compare it to theory, general relativity wins. This is remarkable for a theory developed in 1915, in a world with no computers, no particle accelerators, no space telescopes, no means of imagining that we'd one day receive gravitational signals from events 1.3 billion light-years away. On the failure point side, the singularity exposes general relativity's incompleteness as clearly as anything in physics. The infinities the equations produce at the singularity are not computational artifacts. They're the theory's honest acknowledgement that it breaks down there. Quantum gravity, whatever it is, must take over. And we don't yet have it. The Hawking radiation calculation exposes a different incompleteness. The tension between the second law of thermodynamics, entropy increases, unitarity in quantum mechanics, information is conserved, and the prediction of general relativity that information can be lost inside black holes. These three pillars of physics cannot all be simultaneously correct without modification. Resolving the information paradox will require revising at least one of them. Beyond fundamental physics, black holes have transformed our understanding of galaxy formation and evolution. The M-sigma relation, the tight empirical correlation between black hole mass and stellar velocity dispersion in galactic bulges, holds across many orders of magnitude and was discovered in the late 1990s. It tells us that the black hole at a galaxy's center and the galaxy's stellar population grew together, regulating each other. Models of galaxy formation that ignore black hole feedback produce galaxies that are far too massive and far too actively star-forming compared to what we observe. Models that include AGN feedback, the jets, the radiation, the mechanical energy deposited into surrounding gas, reproduce observed galaxy properties much more accurately. In this sense, the history of the universe as we observe it, the galaxy mass function, the cosmic star formation rate density, the size and color distribution of galaxies bears the imprint of black hole activity across cosmic time. The universe we live in is shaped, in part, by the supermassive black holes at galactic centers that have been heating, stirring, and suppressing star formation since the first galaxies assembled. The equations of general relativity do, in fact, permit wormholes. An Einstein-Rosen bridge, named for Einstein and Rosen, who described it in 1935, is a solution to Einstein's field equations that connects two separate regions of space-time through a tunnel. In the maximally extended Kruskal-Sacchares spacetime for a non-rotating black hole, The complete solution contains not just the exterior universe and the black hole interior, but a second exterior universe connected through a bridge at the singularity. The mathematics is sound. The geometry is valid. A wormhole solution exists. The problem is physical realizability. The Einstein-Rosen bridge of a Schwarzschild black hole closes in zero proper time. Any particle entering the bridge from one side finds the bridge pinching off before it can reach the other side. This isn't a matter of going fast enough, then the closure is geometric, not dynamical. Regardless of speed, no particle can traverse the classical Schwarzschild wormhole. For a wormhole to remain open long enough for a particle to traverse it, the throat must be threaded with material of negative energy density, exotic matter. Negative energy density means a stress-energy tensor with negative components in the time-like direction, material that has less energy per unit volume than the quantum vacuum. Quantum mechanics does produce negative energy densities. The Casimir effect, the measurable attractive force between two uncharged conducting plates placed very close together, arises because the quantum vacuum between the plates has lower energy than the vacuum outside, due to the suppression of certain electromagnetic modes between the plates. Negative energy density, in the Casimir sense, is real and measured. The difficulty: Casimir-type negative energies are extremely small in magnitude, spread over specific geometric configurations, and subject to quantum inequalities. Theorems that bound how large and how long-lived negative energy densities can be. The quantities required to stabilize a macroscopic traversable wormhole exceed what quantum inequalities allow by many orders of magnitude, under any mechanism currently known or plausibly conceivable. Most physicists regard macroscopic traversable wormholes as almost certainly physically impossible, not because the equations prohibit them, but because the energy conditions required seem to be ruled out by quantum mechanics. White holes, time-reversed black holes, from which matter and energy only emerge, face similar issues. They're valid solutions of Einstein's equations. They're violently unstable. Any perturbation converts a white hole to something else almost immediately. They have no known formation mechanism. They exist in the mathematical solution space, but almost certainly not in the physical universe. What lies inside a black hole is not another location in space. The singularity is the end of the story physics can currently tell. Whether quantum gravity will rewrite that ending remains open. At the beginning of this video, I said a black hole is a region of space-time where the escape velocity exceeds the speed of light. Everything since then has been the unpacking of that sentence. We've gone from city-sized event horizons containing a few stellar masses to event horizons larger than our solar system containing 66 billion solar masses. We've established that a clock at 1% above the event horizon ticks at 10% of the rate of a clock in normal space-time. We've established that tidal forces for stellar mass black holes destroy anything that approaches long before crossing the horizon, while for the most massive black holes, the horizon crossing is indistinguishable from any other moment in free fall. We've established that the shadow visible in EHT images is 2.6 times the Schwarzschild radius, that Hawking radiation for M8017 has a temperature of roughly 10^17 Kelvin, that Ton 6/18's evaporation timescale exceeds 10^103 years, that gravitational waves from binary black hole mergers were detected at amplitude 10 Sauker to 21, a fractional length change of less than the size of a proton across 4 kilometers. These numbers are real. They come from measurements, from observational programs that took decades, from calculations verified independently by multiple groups. And then there are the things we don't know. We don't know what the singularity actually is. General relativity predicts infinite curvature. Quantum gravity must resolve this, and we don't have a tested quantum gravity theory. We don't know definitively how information is preserved or lost as black holes evaporate. The information paradox has been open since 1976. Progress has been made, but no consensus answer has been confirmed. We don't know how the first supermassive black holes of 1 billion solar masses formed within the first billion years after the Big Bang. No single formation pathway currently accounts for their masses on the available timescale. We don't know whether primordial black holes exist. We have theoretical motivations and ongoing observational searches, but no confirmed detection. We don't know the full population of isolated stellar mass black holes in the Milky Way. We've confirmed dozens. There may be 1 billion. Every one of these open questions is a direction in which physics is actively working. Every one of them has observational or theoretical programs aimed at it, and every one of them, if answered, will require the development of new tools, mathematical, observational, computational, that will leave the field of physics permanently expanded. That is the deepest thing black holes are. They're not just extreme objects in space. They're markers of the frontier. Every place where our understanding runs out, the singularity, the information paradox, the first black holes. The full galactic population is also a place where the science of the next century will be made. In the Milky Way, the stellar mass black hole population is estimated at between 10 million and 1 billion objects. The uncertainty spans 2 orders of magnitude because the vast majority of these objects are completely invisible. Solitary black holes not actively accreting, emitting nothing, leaving no electromagnetic trace. We've directly confirmed a few dozen, all through binary systems where accretion produces detectable X-ray emission. Isolated stellar mass black holes can be detected through gravitational microlensing, the brief brightening of a background star as the black hole passes in front of it, bending its light. In 2022, a team using Hubble data reported the first strong candidate for an isolated stellar mass black hole detected this way, a dark compact object of 1.6 to 4.4 solar masses drifting through the galactic disk, detectable only by the way it bent the light of a distant background star over a period of about 270 days. This will be the primary detection method for isolated black holes going forward, as large-scale microlensing surveys like the Rubin Observatory's LSST accumulate data on billions of background stars. In the observable universe, approximately 2 trillion galaxies. Each large galaxy contains at least one supermassive black hole. Many contain more from past mergers, even conservatively estimating 100 million stellar mass black holes per galaxy, ectit 10 procan 12 Galaxies x 10 or 8, stellar mass BHs per galaxy. 4, 2x10 20 stellar mass black holes 200 quintillion. In the observable universe alone, which is itself just one Hubble volume in what may be a vastly larger universe. Most are invisible. Most will remain invisible with any technology foreseeable from our current vantage point. The galaxy is full of them. 100 million to 1 billion dark objects drifting through the disk and halo, passing occasionally near a background star and momentarily bending its light, then continuing on in silence. This is the deepest unsolved problem that black holes expose, and it sits at the intersection of the 2 most successful theories in physics. Quantum mechanics contains a principle called unitarity. The total quantum information content of a closed system is conserved. Given the exact quantum state of a system at one moment, the wave functions of all its constituent particles, their entanglements and quantum numbers, you can reconstruct its state at any other moment, past or future. Information is transformed but never destroyed. General relativity predicts that matter falling into a black hole crosses the event horizon and falls toward the singularity. From outside, No signal from inside the event horizon can escape. When Hawking showed in 1974 that black holes emit thermal radiation, the calculation produced a spectrum that carries no information about the specific quantum state of the infalling material. It's random thermal noise, determined only by the black hole's mass, charge, and spin. After the black hole evaporates, the radiation it has emitted encodes nothing about what fell in. This violates unitarity. The quantum state of the infalling matter has been destroyed. One or both of the following must be wrong or incomplete: quantum mechanics unitarity principle or Hawking's calculation of thermal radiation. There are no other options. Resolving the paradox requires either showing that information is preserved in a subtle way that Hawking's calculation missed, or accepting that quantum mechanics must be modified in the presence of gravity. Most theorists currently favor the former. The ADS-CFT correspondence, a mathematical duality between string, theory in a space with negative curvature, anti-D, Sitter space, and a conformal. Quantum field theory on its boundary provides a framework where a black hole has a dual description as a thermal state in a quantum field theory that is manifestly unitary. In this dual description, information is preserved. The black hole's evaporation is a scrambling process that distributes information into correlations across all the outgoing radiation in a form that's practically impossible to decode but theoretically complete. In recent years, calculations within this framework have demonstrated a page curve, the expected behavior of the entanglement entropy of the outgoing radiation over a black hole's lifetime if information is preserved. These calculations, using a combination of the ADS-CFT framework and a new tool called Island Formula, show that the entanglement entropy follows the page curve rather than increasing monotonically as Hawking's original calculation suggested. This is progress. But it's progress within a specific mathematical framework, ADS-CFT, that maps our universe into a slightly different mathematical universe than the one we live in. The question of how precisely this resolves the information paradox in our actual universe, with positive cosmological, constant rather than negative, is still being worked out. The information paradox has been open since 1976. Its resolution will require new physics at the boundary between quantum mechanics and gravity. When it comes, it will be among the most significant advances in fundamental physics in a century. At 5:51 a.m. Eastern Daylight Time on September 14, 2015, two L-shaped detectors 3,000 kilometers apart, one in Livingston, Louisiana, one in Hanford, Washington, simultaneously measured a signal lasting 0.2 seconds. Each detector consists of two 4-kilometer-long arms arranged at right angles with mirrors at the ends. A laser beam is split and sent down both arms simultaneously, reflecting off the mirrors and returning to a detector. When both arm lengths are exactly equal, the returning beams cancel out perfectly through destructive interference. When a gravitational wave passes, it alternately stretches one arm and compresses the other, changing their relative lengths by an amount that the interferometer measures. The change in arm length measured in G1500914, approximately 10^18 meters. 1 atometer, about 1/1000th. The diameter of a proton. To measure a change in 4-kilometer arm lengths of 10 or 18 meters is to measure a fractional change of 2.5x, 1022. This is among the most precise measurements ever made by human technology. The sensitivity is achieved through a combination of high-power lasers, 100 plus watts, suspended mirrors with masses of tens of kilograms cooled to near thermal noise limits, and active seismic isolation systems that decouple the mirrors from vibrations ranging from trucks on nearby roads to distant earthquakes. W1500914's source, two black holes. At the time of merger, approximately 36 and 29 solar masses, spiraling together 1.3 billion light-years away. Their final orbit had a period of a few milliseconds. The gravitational wave signal, a brief chirp rising in frequency from about 35 Hz to roughly 150 Hz over 0.2 seconds, directly encodes the orbit's evolution. Frequency increases as the orbital separation decreases, and amplitude increases as the radiated power increases. The merger produced a final black hole of approximately 62 solar masses. The missing 3 solar masses, the difference between 36 plus 29 and 62, was radiated as gravitational waves in that 0.2-second burst. 3 solar masses of energy, converted entirely to gravitational waves, radiated in 0.2 seconds. The peak luminosity of GW1F0914 in gravitational waves was approximately 3.6 x 1049 watts, more than 50 times, brighter than the total light output of all observable galaxies combined for those 0.2 seconds. Since 2015, LIGO and Virgo have detected over 90 gravitational wave events, binary black hole mergers, binary neutron star mergers, including GU170817, which was simultaneously observed in light across all wavelengths, the first multi-messenger gravitational wave event, and neutron star black hole mergers. The masses of the participating black holes span a wide range, from below 5 solar masses to over 100, with one merger, JW190521, producing a final black hole of approximately 150 solar masses in the intermediate mass range. These observations are not just discoveries about individual objects. Each event is a precision test of general relativity in the strong field, high-velocity regime. The waveforms from each merger are compared against theoretical predictions from numerical relativity, simulations of Einstein's equations on supercomputers, and in every case, the match is excellent. General relativity passes each test. The future, the LISA, Laser Interferometer Space Antenna mission, planned by ESA for the 2030s, will extend gravitational wave astronomy into the millihertz frequency band, the regime of supermassive black hole mergers. When 2 supermassive black holes spiral together and merge, the gravitational wave signal will be in the range LISA is designed for. Events like the eventual merger of Sagittarius A and Andromeda's central black hole, if it happens on a relevant timescale, would produce signals LISA could, in principle, detect from anywhere in the observable universe. We have given ourselves ears tuned to the vibrations of space-time, and every chirp we hear is a black hole announcing itself across distances and time scales that would have seemed fictional a generation ago. The primary feeding mechanism is accretion. Gas from a galaxy's interstellar medium drifts toward the central black hole under gravity, but angular momentum prevents it from falling straight in. Instead, it forms a rotating disk, the accretion disk, within which material gradually migrates inward as turbulence, driven primarily by the magneto-rotational instability, which amplifies magnetic field perturbations in conducting plasma, redistributes angular momentum outward. As material moves inward through the disk, gravitational energy converts to heat. At the innermost stable circular orbit, 3 Schwarzschild radii for a non-rotating black hole, material plunges inward and is lost. The luminosity radiated by the disk represents a conversion of gravitational energy to radiation with an efficiency of roughly 6% for a non-rotating hole and up to 42% for a maximally rotating one. For comparison, hydrogen fusion in a star converts less than 0.7% of the rest mass energy to radiation. A maximally spinning black hole. Accretion disk is 60 times more efficient than stellar hydrogen burning, the maximum sustainable luminosity before radiation. pressure prevents further accretion is the Eddington luminosity. LED Ikshak 4 pgmmPCSS, where MP is the proton mass and SIT is the Thomson scattering cross-section. This scales linearly with black hole mass. For a 10^9 solar mass black hole, LED 1.3 x 10^47 ergs per second, roughly 3 trillion times the sun's luminosity. Quasars, the most luminous persistent objects in the universe, are black holes accreting near or above the Eddington rate. TON 618 was, at its observed epoch, radiating at approximately 4x 10^47 ergs per second, making it brighter in a single point than the combined light of every star in the observable universe, combined within a much larger region. Alongside steady accretion, episodic tidal disruption events, TDEs, represent a more dramatic feeding mode. A TDE occurs when a star's orbit brings it within the tidal radius of a black hole. RT, R star, MBHN M star 113. Inside this radius, tidal forces across the star exceed the star's self-gravitational binding energy. The star is disrupted, torn apart over days to weeks. Roughly half the stellar debris is gravitationally bound to the black hole and returns to form a temporary, highly eccentric accretion stream. The other half escapes to infinity on hyperbolic trajectories. The resulting TDE flare can briefly reach or exceed Eddington luminosity, producing a transient brightening of a previously quiescent galactic nucleus visible across billions of light years. We've now cataloged hundreds of TDE candidates from wide-field transient surveys, and they provide our best direct observations of black holes consuming large masses in real time. The most extreme TDEs produce relativistic jets as well as thermal disk emission. Swift J1644 PLA 7, 2011, produced a jet pointed almost directly toward Earth, detectable in gamma rays for weeks. Our own SGR Eos has not recently disrupted a star, but it shows daily X-ray flares, brief brightenings by factors of a few to 100, likely produced by small amounts of gas spiraling inward from the surrounding stellar environment. The Fermi bubbles, discovered in 2010, suggest SGR Eos was significantly more active several million years ago, a past feeding episode that inflated two enormous lobes of high-energy emission extending 25,000 light-years above and below the galactic plane. Sagittarius A sits at the Milky Way's center, 26,000 light-years from Earth, with a mass of 4.1 million solar masses and a Schwarzschild radius of approximately 12.1 million kilometers. It is by mass a modest supermassive black hole. By significance to us, it's unique. The case for its existence was built over decades through one of the most technically demanding observational programs in astronomical history, tracking the orbits of individual stars at the galactic center. The galactic center is obscured at visible wavelengths by dust in the galactic plane. It becomes accessible in infrared and radio where dust is transparent. Starting in the 1990s, two groups, one led by Reinhard Genzel at the Max Planck Institute for Extraterrestrial Physics, one led by Andrea Ghez at UCLA, began monitoring stars within a few arc-seconds of the radio source SGRA using infrared adaptive optics cameras that corrected for atmospheric blurring in real time. Over years, they tracked dozens of stars, the S-star cluster, executing elliptical orbits around the galactic center. The star S2, also cataloged as S02, became the key reference, a star about 15 solar masses, completing a full orbit around SGR-8 every 16-17 years. Its orbit carries it to a closest approach of 120 AU, its pericenter, at which point it moves at 7,650 kilometers to 2.55% of the speed of light. The orbital shape, period, and velocity at pericenter, combined via Keplerian orbital mechanics, give the mass of the central object. The answer from S2's orbit, 4.1 to 4.3 million solar masses, within a region smaller than its pericenter distance of 120 AU. No known configuration of ordinary matter, no cluster of stars, no exotic but visible object type can concentrate that much mass in that small a volume. The only consistent explanation is a supermassive black hole. S2's orbit also allowed a test of general relativity. At pericenter, moving at 2.55% of light speed in a strong gravitational field, S2's orbit shows a precessing apsidal motion. The orbit itself rotates slightly with each pass, exactly as Einstein's equations predict for a test mass in Schwarzschild geometry, measured and confirmed. For this work, the first compelling observational demonstration of a supermassive compact object at the galactic center, Genzel and Ghez shared the 2020 Nobel Prize in Physics. In 2022, the Event Horizon Telescope collaboration published the first direct image of SGRA. The imaging was technically more challenging than M87 because SGRA is smaller. The angular size of the shadow is similar to M87. Despite the mass difference, because SGRA is much closer, and because the interstellar plasma between us and the galactic center scintillates, fluctuates in density rapidly enough to blur the image on observation timescales. The EHT team developed averaging techniques to extract a time-averaged image from the variable signal. The result, an orange and black ring, structurally similar to M87 Keck, with the shadow diameter consistent with a 4.1 million solar mass Schwarzschild black hole, another successful test of general relativity in the strong field regime. The angular size of M87T's shadow is approximately 42 micro-arcseconds, 42 millionths of 1 arcsecond, where an arcsecond is 1/3600th of a degree. For comparison, the full moon subtends about 1/800 arcseconds. M87T's shadow is about 43 million times smaller in angular size than the moon. Resolving this requires a telescope with angular resolution of a few micro-arcseconds. The resolution of a telescope depends on the ratio of the observing wavelength to the telescope diameter. More precisely, angular resolution, LD, where L is wavelength and D is diameter, at radio wavelengths near 1.3 millimeters, chosen because the galactic center and M87 are most transparent at this wavelength. Achieving micro-arcsecond resolution requires L-Tho 13 mm, 5 x 10^12 irradians, 2.6 x 10^8 meters, 260,000 kilometers more than 20 times Earth's diameter. A single dish this size is not buildable. The Event Horizon Telescope collaboration linked existing radio observatories across the world using Very Long Baseline Interferometry, VLBI. Telescopes in Hawaii, Arizona, Chile, Spain, Mexico, and Antarctica participated. The maximum baseline, the longest distance between any two telescopes, is roughly the diameter of Earth, about 12,700 kilometers. This falls short of the ideal aperture, but with careful sampling of many different baselines and sophisticated image reconstruction algorithms, the sparse aperture data yields an image. Each telescope recorded data at approximately 2 gigabits per second onto custom hard drives, synchronized by hydrogen maser atomic clocks accurate to a few hundred femtoseconds. The South Pole. Telescope's data couldn't be transmitted over the internet. Antarctica has no connection with the bandwidth needed for petabytes, so it was physically shipped by cargo aircraft after winter ended. The total data volume from the 2017 M87 campaign approximately 5 petabytes. At the data processing stage, 4 independent teams applied different image reconstruction algorithms to the same data and compared results. The consistency between independent methods was the primary validation that the orange ring in the final image was a real astronomical structure, not an artifact of any particular reconstruction approach. April 10, 2019, the image published. A blurry but unmistakable orange ring. The photon ring of M87T, with a dark central shadow matching the predicted size for a 6.5 billion solar mass black hole to within uncertainties. General relativity, tested in a regime of extreme gravity at cosmological distance, produced an answer that matched observation. May 12, 2022, SGRA imaged. Our black hole, the object at the center of our galaxy, the one whose gravity S2 orbits, photographed directly for the first time. 2 images. Each one required years of planning, international coordination across dozens of institutions, the development of new algorithms, and the physical transport of petabytes of data from remote observatories. Both images match the predictions of a theory written in 1915 by a person who had never heard the term black hole. The Event Horizon Telescope image published in April 2019, the first photograph of a black hole's shadow, shows an orange and black ring, blurry at the resolution achieved, with a bright ring of light surrounding a dark central region. This is not exactly what you'd see with your eyes up close, but it captures the essential visual structure correctly. Let's build the visual from physics. A black hole emits no light directly, by definition. What makes it visible is its effect on the light around it. Start with the shadow. Every photon approaching the black hole on a path that would take it inside the photon sphere at 1.5 Schwarzschild radii either enters the event horizon or orbits and eventually falls in. No photon from inside this radius reaches a distant observer. So the observer sees a dark region, the shadow, whose apparent angular size is determined by which photon trajectories are captured versus escape. The shadow's apparent radius is not equal to the Schwarzschild radius. It's approximately 2.6 times the Schwarzschild radius, because photons that arrive from just outside the photon sphere can still be deflected enough to escape, but contribute to a brightening just outside the dark region. The photon ring surrounds this shadow. Light from the accretion disk, and from all other bright sources on the far side of the black hole, follows curved paths around the black hole, bending through partial or complete orbits before escaping outward. Photons that complete half an orbit around the black hole arrive at the observer from directions that appear to surround the shadow, forming a bright ring. Multiple subrings exist, corresponding to photons completing 1, 1.5, 2, 2.5 orbits, each successively thinner and brighter in principle, but only the outermost one is detectable at current resolution. The accretion disk, when present, adds the dominant visual feature for most active black holes. Material in the inner disk reaches temperatures of millions of degrees, emitting primarily in X-rays, while material at larger radii cools to ultraviolet, visible, and infrared. The disk is turbulent, magnetically threaded, and in the inner regions, relativistic. Material at the innermost stable circular orbit, 3 Schwarzschild radii for a non-rotating black hole, moves at a significant fraction of the speed of light. When viewing an accretion disk edge-on, gravitational lensing bends the light from the far side of the disk around the top and bottom of the black hole's shadow, producing the distinctive wraparound appearance depicted in Interstellar. This is physically accurate. Kip Thorne, who consulted on that film, made sure of it. The approaching side of the disk is also significantly brighter than the receding side due to Doppler boosting, the same effect that makes an ambulance siren sound higher as it approaches and lower as it recedes. But applied to light, this brightness asymmetry is visible in the M87 image. The southern arc of the photon ring is brighter than the northern arc, because the southern side of M87T's accretion flow is moving toward us, the net visual of a black hole with an active accretion disk, a dark central shadow, surrounded by a bright lensed ring of emission, with one side brighter than the other, sometimes with jets extending outward along the polar axis, sometimes with a complex warped disk structure if the black hole's spin axis is misaligned with the disk. Some black holes don't only pull material in, they launch material outward, at velocities approaching the speed of light, in beams that can extend for millions of light years. The mechanism operates as follows. Most black holes carry angular momentum, spin, inherited from the rotating material that formed or fed them. A spinning black hole drags space-time around it in a phenomenon called frame dragging. The rotation of the black hole literally twists the geometry of the surrounding space-time, pulling it along in the direction of rotation. The accretion disk surrounding an active black hole is threaded with magnetic field lines, generated by the plasma's own motion and frozen in by the high electrical conductivity of the plasma. As material in the inner disk spirals toward the event horizon, the combination of disk rotation and frame dragging twists these magnetic field lines into a helical structure, like winding a spring. The energy stored in this twisted magnetic field, combined with the angular momentum it can extract from the black hole itself through the Blanford-Zanajek mechanism, accelerates plasma from the inner disk outward along the rotation axis. The result is a relativistic jet, a narrow beam of plasma, moving at 99% or more of the speed of light, extending outward along the black hole's poles. The jet from M87Ho, approximately 6,500 light-years long, 6,500 light-years. This single jet, powered by a single black hole, extends across a distance that light takes 6,500 years to cross. The total power carried by the M87 jet is estimated at roughly 1044 watts, comparable to the combined light output of the Milky Way. These jets do not operate in isolation. They push into the surrounding galaxy and, in massive galaxies with hot gas halos, into the surrounding intracluster medium. Observations in X-ray wavelengths show enormous cavities, bubbles, in the hot gas surrounding active galactic nuclei, AGN, carved by the mechanical energy of jets that inflate and then detach. These bubbles can be hundreds of thousands of light-years across. The energy deposited by these jets into surrounding gas has a direct impact on galaxy evolution. Gas that would otherwise cool, condense, and collapse into new stars is kept hot and diffuse by jet heating. The most massive galaxies in the universe, the giant ellipticals at the centers of galaxy clusters, maintain lower star formation rates than their gas supply would suggest, because their central black hole's jets continuously heat the available material. The mass of a galaxy's central black hole correlates tightly with the velocity dispersion of its stellar bulge, the M-sigma relation, observed across galaxies from dwarf ellipticals to the most massive BCGs. This correlation spans 5 orders of magnitude in black hole mass and is one of the strongest empirical evidence that black holes and their host galaxies co-evolve, each regulating the other's growth through a feedback loop mediated by accretion, jets, and radiation. In 1974, Stephen Hawking combined quantum field theory with general relativity and found a result that surprised him as much as everyone else. Black holes must radiate. The derivation begins with quantum mechanics' description of the vacuum. Empty space in quantum field theory is not empty. The quantum vacuum is permeated by fluctuations, virtual particle-antiparticle, pairs that spontaneously appear and annihilate on timescales, constrained by the Heisenberg uncertainty relation det/dt. 2. These pairs exist too briefly to be observed directly, but they have measurable effects. The Casimir effect, the Lamb shift, the anomalous magnetic moment of the electron, all measured to extraordinary precision. Near the event horizon of a black hole, a virtual pair can be split. One particle of the pair falls inside the event horizon. The other escapes outward. The escaping particle carries positive energy and becomes real radiation. The infalling particle carries negative energy in the reference frame of a distant observer and reduces the black hole's total mass energy. The net effect, the black hole loses mass, and an outside observer receives radiation. This Hawking radiation has a thermal spectrum. It looks like the radiation from a black body at temperature T-car-free C3 8 pgmkb. Where is the reduced Planck constant? C is the speed of light, G is Newton's gravitational constant, and Kb is Boltzmann's constant for a 10 solar mass black hole. 6x10, 9K. 6 billionths of a degree above absolute zero. The cosmic microwave background, the ambient radiation filling all of space, left over from the Big Bang, currently has a temperature of 2.725 K, a stellar mass. Black hole's Hawking temperature is 450 million times colder than the CMB. The black hole currently absorbs more energy from the CMB than it radiates via Hawking radiation, so its mass is actually increasing, marginally. Only when the universe expands and cools to below the black hole's Hawking temperature, far in the future, will net evaporation begin. The evaporation timescale is proportional to M3 10 evap. 5120 PG2 M3 C4 4A 10 solar mass stellar black hole, approximately 2x 1074 years. The universe's current age is 138x 10 or 10 years. This stellar black hole would require about 1.4x 10^64 times longer than the universe's current age to evaporate. For TON 618 at 66 billion solar masses. The evaporation timescale scales as M3, placing it at roughly 10^103 years. For comparison, the estimated number of atoms in the observable universe is about 10^80. The evaporation timescale of TON 618 exceeds the number of atoms in the observable universe, expressed in years. As a black hole evaporates, its mass decreases, its temperature increases, and its evaporation accelerates. The final moments of evaporation, when the black hole's mass reaches Planck scale values of about 2 × 10^8 kilos, involve physics that requires a full theory of quantum gravity to describe. What we can say is that the final burst of Hawking radiation carries very high energy, and that after the evaporation is complete, no horizon remains. Whatever fell in, all the mass, all the information encoded in the infalling matter has been returned to the universe in some form over an almost incomprehensible span of time. This is one of the deepest properties of black holes. They are not eternal. They end. They give back. Just not on any time scale that should concern anyone reading or listening to this on any planet that currently exists. In 1905, Einstein published special relativity. In 1907, extending that framework to include accelerating reference frames, he derived the equivalence principle. The effect of gravity is locally indistinguishable from the effect of acceleration. This led him to the prediction, confirmed by 1919, that gravity bends light, and it also led to a prediction about time. Gravity slows it. Gravitational time dilation is not a metaphor. It's a measured, quantified, technologically consequential fact. The GPS satellite network provides the clearest everyday demonstration. GPS satellites orbit at an altitude of roughly 2,200 kilometers. At that altitude, two time dilation effects operate simultaneously. The satellites move fast relative to the Earth's surface, about 14,000 kilometers per hour, which slows their clocks by special relativistic time dilation. Moving clocks run slow. But they're also at a higher altitude, where Earth's gravity is weaker, which speeds their clocks up by gravitational time dilation. Weaker gravity means less time dilation, so clocks there run faster relative to those at Earth's surface. The net result, satellite clocks run fast by approximately 38 microseconds per day relative to ground clocks. GPS works by measuring timing differences at the nanosecond level, billionths of a second. 38 microseconds is 38,000 nanoseconds. Without relativistic corrections, GPS positional errors would accumulate at about 10 kilometers per day, rendering the system useless within hours of launch. Every GPS receiver on Earth is running relativistic corrections in real time. Gravitational time dilation is built into the technology you use to navigate. Near a black hole, the effect is taken to extremes that no other environment in the universe can match. The gravitational time dilation factor for a clock at radius r around a Schwarzschild black hole is local, t, distant, 1 r SAR, where rs is the Schwarzschild radius, at twice the Schwarzschild radius. 1 to 2, reader 0.707. Your clock runs at 70.7% of the rate of a distant clock. For every 10 seconds that pass for you, 14.1 seconds pass for someone far away at 10% above the event horizon. 111.1 or 0302. Your clock runs at 30% of the distant rate, at 1% above the event horizon. 11101, 0.0995, about 10% of the distant rate. For every second you experience, roughly 10 seconds pass in the far universe. At the event horizon itself, 1100, your clock, from the perspective of a distant observer, has stopped. From your own perspective, nothing unusual is happening with time. A second is still a second. Your thoughts occur at their normal pace. This is the key. Time dilation is always a statement about the relationship between two observers, not about what any single observer experiences internally. What a distant observer sees is an object approaching the event horizon, slowing in apparent motion, its light increasingly redshifted, photons losing energy climbing out of the gravitational field, until it appears frozen, growing darker and redder, essentially invisible. The infalling observer, from their own frame, crosses the horizon normally and continues. The practical upshot. If you could somehow orbit very close to a supermassive black hole's event horizon for what felt to you like a year, then escape and return to the outer universe, you'd find that far more time had passed outside. How much more depends on how close you were. Orbiting at 1% above the event horizon for a subjective year would correspond to roughly 10 years passing in the outer universe. At 0.1% above 100 years. At 0.01% above 1,000 years. The mathematical structure allows this kind of forward time travel without any violation of known physics. It's an effect of existing in a region where the geometry of space-time is extremely curved. General relativity makes a specific prediction about what's inside the event horizon of a black hole. A singularity. In the context of differential geometry and physics, a singularity is a location where a mathematical quantity takes an infinite value. At the singularity of a non-rotating, Schwarzschild black hole, the space-time curvature diverges to infinity. Density diverges to infinity. The equations of general relativity return outputs that cannot be interpreted. Division by zero. infinite stress energy tensors, and cease to provide physical predictions. This is not a computational difficulty. It's a signal from the mathematics that the theory has been pushed outside its domain of applicability. General relativity cannot describe what happens at the singularity, and it knows it. The divergence to infinity is the theory's own indication that something beyond itself is needed there. What's beyond general relativity? Quantum mechanics. More precisely, a theory of quantum gravity, a framework that unifies the two greatest theories in modern physics. General relativity describes gravity and space-time geometry on large scales. Quantum mechanics describes the behavior of matter and energy at small scales. At the singularity, both scales converge. Extreme mass energy density concentrated in an arbitrarily small region requires both frameworks simultaneously. We don't have a working, unified theory. The leading candidates are well-developed but not fully verified string theory proposes that fundamental particles are not points but one-dimensional, vibrating strings, and that the apparent singularity in black holes is an artifact of applying point-particle physics beyond its range. In string theory, the singularity is resolved, replaced by a high-energy but finite-density region where string dynamics dominate. The equations produce finite outputs. Loop quantum gravity discretizes spacetime itself, proposes that spacetime is not smooth and continuous but composed of finite, indivisible quanta of area and volume at the Planck scale, approximately 1.6 x 10 order 35 meters. At this scale, the singularity becomes a region of extremely high but finite energy density. Some loop quantum gravity models predict a quantum bounce, where the infalling matter reaches the Planck density and then rebounds, potentially creating an expanding region of spacetime on the other side, a baby universe. In some formulations, both theories are mathematically sophisticated and internally consistent. Neither has produced a confirmed experimental prediction that distinguishes it from the other, or from the classical singularity prediction of general relativity in any test we've been able to perform. The honest summary: at the center of every black hole, there is something we cannot currently describe. General relativity ends there. Quantum mechanics, extended to that regime, hasn't yet produced a consensus answer. The singularity is the most prominent advertisement in physics for the fact that our understanding of the universe, however impressive, is incomplete. This matters beyond black holes themselves. Whatever resolves the singularity, whatever quantum gravity theory, eventually describes what happens. There it will be the most fundamental advance in physics since quantum mechanics was developed in the 1920s. The singularity problem is not a detail. It's the central unsolved problem of fundamental physics. The tidal force on an object in a gravitational field arises because gravity varies with distance. A point closer to a gravitational source is pulled more strongly than a point farther away. Across any extended object, this creates a differential force, stretching the object along the radial direction toward the source and compressing it from the sides. The mathematical expression for tidal acceleration across an object of length L at distance r from a mass m is a tidal. 2gmlr3, the r3 denominator is critical. Tidal force grows with the cube of proximity. Get 10 times closer and tidal force becomes 1,000 times stronger. This is why tidal forces near stellar mass black holes are lethal far outside the event horizon. For a 10 solar mass black hole and a 1.7 meter tall human body, at 1,000 kilometers from the center, atidal 8 x 10·6 m², about 800,000 g of differential acceleration. Every structural element of your body fails simultaneously. You cease to exist as an organized system. At 100 kilometers, still well outside the 29.5-kilometer event horizon. A tidal 8x10^9m(s2). The energy required to maintain molecular bonds is dwarfed by the differential force. You are atoms moving at different velocities at the event horizon itself. MS2, nuclear binding energies become relevant. Differential forces at this scale approach the energies that hold protons and neutrons together. The stream of what was once a person arrives at the event horizon of a stellar mass black hole as a filament of plasma, progressively thinner as it falls through the final kilometers, coiling into the event horizon and disappearing. For a supermassive black hole like TON 618, the situation inverts. The tidal force at the event horizon scales as 1 to bar Wem 2. At TON 618's event horizon, Schwarzschild radius, 196.7 billion kilometers, the tidal acceleration across a 1.7-meter body is approximately a tidal 5x den 0 den ms2. Earth's surface gravity is 9.8 ms2. The tidal force across your body at TON 618's event horizon is roughly 20 billion times less than Earth's surface. Gravity, completely undetectable by any biological sensor. You could fall through the event horizon of the largest known black hole without any physical discomfort. But inside the event horizon, spaghettification is deferred, not canceled. As you fall toward the singularity, the curvature increases. Tidal forces grow. Eventually, somewhere in the vast interior, the tidal acceleration exceeds what any structure can withstand. The singularity itself represents infinite tidal force. Everything that falls in is eventually spaghettified. To cross TON 618's event horizon from one side to the other, traveling at the speed of sound in air, 343 meters per second, would take roughly 36,000 years. At the speed of a commercial aircraft, 900 km/h, about 49,000 years. At the speed of Voyager 1, 61,000 km/h, about 724 years. At the speed of light, about 15.2 days. Light, the fastest thing in the universe, needs more than 2 weeks to cross the diameter of this black hole's event horizon. Now, 66 billion solar masses expressed differently. The Milky Way contains approximately 100 to 400 billion stars. TON 618's black hole has a mass equivalent to 66 billion stars like our sun. That's roughly the equivalent mass of the entire Milky Way. All of it. Every star, compressed and fed into one black hole. And here's the detail that takes this from large to strange. The average density within TON 618's event horizon is approximately 0.0002 kilograms per cubic meter. The density of air at sea level is about 1.2 kilograms per cubic meter. The average density within the event horizon of the largest known black hole is about 6,000 times less dense than the air you're breathing. You could cross the event horizon of TON 618 and the space-time you're entering per unit volume is less dense than air. The extremity is in the geometry, in the curvature, in the gravitational gradient, in the way every future directed path leads inward, not in any sense of the interior being packed with matter. This is not the largest black hole in the universe. It's the largest one we've measured so far, in the small fraction of the observable universe we've cataloged in detail. Given that the observable universe contains 2 trillion galaxies, and we've measured precise black hole masses for a tiny fraction of them, the largest black holes in existence are almost certainly far more massive than anything currently confirmed. The event horizon is the boundary at which escape velocity equals the speed of light. That much we've established. But there's a deeper aspect to what the event horizon is, geometrically, physically, that most descriptions skip over. And understanding it changes how you think about everything we're going to discuss afterward. The event horizon is a feature of space-time, not a feature of matter. There's nothing at the event horizon. No wall, no surface, no material of any kind. If you were falling toward a supermassive black hole and you crossed the event horizon, no local measurement would tell you it happened. The density of matter at the event horizon is, as we just discussed for TON 618, extremely low. The gravitational field is strong, but not infinitely strong at that boundary. The divergence to infinity happens at the singularity, not the event horizon. Locally, right at the event horizon, space-time looks like space-time. Nothing unusual is happening at that precise location. What's unusual is the global structure. What you're crossing means for every possible future path available to you. General relativity describes gravity as the curvature of space-time. Mass curves space-time around it, and what we experience as gravitational force is actually the response of objects moving through this curved geometry. In the absence of gravity, objects travel in straight lines through space-time. With gravity, they follow curved paths, curved because the geometry they're moving through is curved. Near a black hole, this curvature becomes extreme. And at the event horizon, it becomes extreme in a specific way. All future directed paths through space-time, every trajectory an object can take without violating the laws of physics, curve inward toward the singularity. There are no future directed paths that lead outward. Inward is not a direction in space for an object inside the event horizon. It's the direction of time. The singularity isn't somewhere you'd go if you traveled toward it. It's somewhere you'll be, in the same way that tomorrow is somewhere you'll be, unavoidable without violating causality. This is why the event horizon is a point of no return. It's not because some force prevents escape. It's because escape is geometrically impossible. All the geometric paths that physics allows lead inward. Now, the name event horizon comes from the physics concept of a horizon, the boundary past which events cannot send you information. Just as the visual horizon on a flat plane represents the limit beyond which you cannot see because light from there hasn't reached you, the event horizon of a black hole represents the limit beyond which events cannot send any signal to the outside universe. Whatever happens inside the event horizon is causally disconnected from the rest of space-time. The Schwarzschild radius of the event horizon has a clean formula, R2GMC2. This relationship is linear, double the mass, double the event horizon radius. But volume scales as the cube of radius, so the average density inside the event horizon scales as mR3, mm3, 1m2. As black hole mass increases, the average density inside the event horizon decreases with the square of the mass. This is why TON 618's interior is less dense than air. Its mass is so enormous that its event horizon is correspondingly enormous, and the vast volume inside dilutes the enclosed mass to densities far below what we'd naively expect. The photon sphere sits at 1.5 times the Schwarzschild radius, the radius at which a photon can orbit the black hole in a circular path. These orbits are unstable. Any perturbation sends the photon either spiraling in or escaping outward. But photons that pass near this radius can be deflected into curved paths, completing partial orbits before escaping. And this is what produces the photon ring visible in EHT images. The shadow visible in those images, the dark central region, is not the event horizon directly. Its apparent radius is roughly 2.6 times the Schwarzschild radius, because photons from behind the black hole are bent around it and still escape, while photons from the forward direction that pass within a certain radius are captured. The shadow is larger than the event horizon. The experience of approaching a black hole depends almost entirely on which type. The physics here is non-negotiable and precise. and the counterintuitive result it produces is one of the strangest in astrophysics. The most extreme black holes are, in a specific physical sense, the gentlest to approach. Approaching a stellar mass black hole. Take a 10 solar mass black hole. Event horizon radius 29.5 kilometers, tidal forces, the differential gravity across the length of an object, scale as mr3, where r is your distance from the center. At 10,000 kilometers from the center, the tidal acceleration across a human body, approximately 1.7 meters tall, is already on the order of 10⁵ ms2, 10,000 times Earth's surface gravity, acting differentially across just 1.7 meters of your body. Catastrophic structural failure of biological tissue. At 1,000 kilometers, 10.08 ms2 differential. Your molecular bonds begin to fail. At 100 kilometers, still, 3 times farther than the event horizon. The tidal acceleration exceeds 1011 ms2. Every particle of your body is accelerating at a different rate depending on its distance from the black hole. Your material disintegrates into a stream, stretching along the radial direction, compressing from the sides, thinning into a filament. This is spaghettification, and for a stellar mass black hole, it happens far outside the event horizon. The stream of particles that was once a person arrives at the event horizon as a thread of matter a fraction of a millimeter thick but thousands of kilometers. Long approaching TON 618, the tidal force at the event horizon scales as on M2. For a black hole as massive as TON 618, the tidal force across a human body at the event horizon is approximately 5 × 10^10 nms2, about 1 billion times less than Earth's surface gravity, acting differentially, imperceptible. Your body experiences no unusual forces at all. You cross the event horizon. Nothing marks the moment. No physical sensation. The space-time right there is locally unremarkable. You could be reading a book and not know you'd crossed. What changes is your future. You're now in a region where every geometric path leads toward the singularity. From outside, light can still reach you. The event horizon only prevents things from escaping outward. It doesn't prevent inward-directed light from reaching you. So the outside universe remains visible, but increasingly distorted. The entire observable universe appears compressed into a shrinking bright disk above you, while below is darkness, the singularity, geometrically ahead of you in time. How long do you have? The infall time from the event horizon to the singularity for a Schwarzschild black hole is approximately 10 max PM in natural units. For TON 618, this works out to several days of proper time. Days to observe, measure, think. Days inside the most extreme environment known in the universe. Days that, from the outside, appear to last an infinite amount of time due to gravitational time dilation. Eventually, somewhere between the event horizon and the singularity, as the space-time curvature increases from tolerable to infinite, tidal forces become lethal. The singularity isn't something you approach. It's a moment in your future, and it arrives. And at the center of some long-faded supernova remnant, somewhere in the Milky Way, the black hole that formed that day is still there, silent, dark, waiting for whatever eventually wanders close enough. The word black hole refers to a category, and the range within that category is so large that objects at opposite ends of it barely seem related. Understanding the full range matters, because scale is the entire point of this video. Stellar mass black holes are the type we've been discussing, formed from the deaths of massive stars, ranging from roughly 3 solar masses at the minimum up to perhaps 100 solar masses for the most extreme stellar collapses. Their event horizons range from about 9 kilometers in radius at the low end to roughly 300 kilometers at the high end. These are the most common type. distributed throughout galaxies in enormous numbers, mostly invisible unless they're actively consuming material from a companion star. Intermediate mass black holes sit in the range between 100 and 100,000 solar masses. They've been theorized for decades but remain the hardest type to confirm observationally because they don't fit cleanly into either the stellar collapse formation channel or the conditions that produce supermassive black holes. The leading formation scenarios involve repeated mergers in dense stellar clusters, either young massive star clusters or ancient globular clusters, where stellar collisions and black hole mergers can build up mass over millions of years. In 2024, strong evidence emerged for an intermediate mass black hole of approximately 8,200 solar masses at the center of Omega Centauri, the most massive globular cluster orbiting the Milky Way. Their event horizons range from hundreds to millions of kilometers in radius. Supermassive black holes are the giants at galactic centers. Every large galaxy we've studied contains one. They range from roughly 1 million solar masses to tens of billions. Their formation is one of the great open questions in astrophysics. The universe is only 13.8 billion years old. Yet we find black holes of 1 billion solar masses or more in the first billion years after the Big Bang, which is extremely difficult to account for even with the most favorable models of rapid accretion and repeated merging. Their event horizons range from tens of millions of kilometers to hundreds of billions of kilometers. Primordial black holes are speculative, not yet confirmed, but theoretically well motivated. In the first fractions of a second after the Big Bang, density fluctuations in the primordial plasma could have been large enough in certain regions to cause direct gravitational collapse, producing black holes across a wide mass range depending on the timing and scale of the fluctuation. Primordial black holes below roughly 10-12 kilograms would have fully evaporated through Hawking radiation by now. Those above that threshold would still exist. Some models suggest that primordial black holes in a certain mass window, from asteroid to small planet masses, could account for a fraction of the universe's dark matter. Several observational programs are actively searching for them through gravitational microlensing effects. 4 types. Mass ranging from grams theoretically to 66 billion solar masses confirmed. The same physics, the same event horizon equation, operating across this entire range. Let's build the scale of stellar mass black holes from the ground up, using specific objects. The minimum mass stellar black hole sits at approximately 3 solar masses. Schwarzschild radius 8.9 kilometers. Diameter 17.8 kilometers. 17.8 kilometers. The width of a medium-sized city. The length of Manhattan from end to end. A marathon runner could cross its diameter in under 2 hours. If running in a straight line across the event horizon of this object, which contains 3 times the mass of the Sun. The Sun is 1,192,000 kilometers in diameter. We've just taken 3 of those and compressed them into a sphere 18 kilometers across. Cygnus X1 is the first confirmed black hole, discovered in 1964 in the constellation Cygnus via its intense X-ray emission, which comes from material stripped off its companion star and heated as it spirals inward. Its mass, approximately 21 solar masses. Schwarzschild radius, approximately 62 kilometers. Diameter, 124 kilometers. About the width of the island of Puerto Rico. A commercial aircraft at cruising speed crosses its diameter in about 15 minutes. GRS 1915 plus 105. Approximately 12 solar masses. Event horizon diameter, roughly 71 kilometers. V404, Cygni, about 9 solar masses. Event horizon diameter, approximately 53 kilometers. GW 15014. The 2 black holes that merged and were detected as gravitational waves in 2015 had masses of 36 and 29 solar masses before the merger, producing a final black hole of approximately 62 solar masses. Event horizon diameter of the final merged object, approximately 365 kilometers. About the width of Iceland. At the upper end of the stellar mass range, pushing toward 100 solar masses, the event horizon diameter reaches roughly 590 kilometers, the distance from Paris to Brussels, the width of Colorado. A supersonic jet crosses it in about 30 minutes. This sphere, 590 kilometers in diameter, contains 100 solar masses. In the middle of it is a singularity, a point of mathematically infinite density, surrounded by roughly 300 kilometers of extreme space-time curvature. The object itself, the black hole, is that sphere. That's what we're describing. A region of space less than the width of Colorado, inside which the escape velocity exceeds the speed of light, inside which time runs backward, relative to any useful definition of forward, inside which a singularity sits at the center in a region our physics cannot describe, and this is the smallest category, Sagittarius AE. The supermassive black hole at the center of the Milky Way has a mass of 4.1 million solar masses. Schwarzschild radius approximately 12.4 million kilometers. Diameter 24.8 million kilometers. That diameter, 24.8 million kilometers, is about 17.8 times the diameter of the Sun. If Sagittarius AS were centered at our Sun's location, its event horizon would extend outward in all directions, encompassing a sphere with a radius more than 17 times the Sun's physical size. Mercury's orbit has a radius of 57.9 million kilometers, so the event horizon would reach about 43% of the way to Mercury's orbit. The S2 star, one of the stars we've tracked orbiting, SGR-A, reaches a closest approach of 120 astronomical units. The event horizon of SGR-A sits at roughly 0.08 astronomical units. The orbit of S2 is still 1/1500 times larger than the event horizon at its closest point. Yet S2 moves at 7,650 kilometers per second at that approach, 2.55% of the speed of light, purely from orbital dynamics around this object. Move up to Andromeda's central black hole. Approximately 150 million solar masses, the midpoint of its estimated range. Schwarzschild radius, 443 million kilometers. Diameter, 886 million kilometers. Mars orbits the Sun at 228 million kilometers. This black hole's event horizon diameter exceeds Mars's orbital diameter by a factor of nearly 4. Centered on our Sun, its event horizon would extend past Mars and most of the asteroid belt. Now, M87 Cow, 6.5 billion solar masses. The most famous black hole we have, the first one ever photographed. Schwarzschild radius, 19.2 billion kilometers. Diameter, 38.4 billion kilometers. Neptune, our solar system's outermost planet, orbits at 4.5 billion kilometers. The event horizon diameter of M87 Tex is 8.5 times the diameter of Neptune's orbit. Every planet in our solar system, Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune, every moon, every dwarf planet, the entire asteroid belt, the Kuiper Belt's inner edge, all of it fits inside M87T's event horizon with an enormous margin. Voyager 1, humanity's most distant spacecraft, launched September 5, 1977, traveling continuously outward at approximately 61,000 kilometers per hour for nearly 50 years, had covered about 23 billion kilometers from Earth by the mid-2020s. Voyager 1 would still be inside M87T's event horizon. M87 is not the largest known black hole. TON 618 is a quasar, an extraordinarily luminous galactic nucleus powered by a voraciously feeding black hole, located 10.4 billion light-years from Earth. Its black hole carries a mass of approximately 66 billion solar masses. Schwarzschild radius 196.7 billion kilometers. Let's build this in layers. 1. Astronomical unit, AU, is the average distance from Earth to the Sun, 150 million kilometers. Ton 6/18's event horizon, radius 196.7 billion kilometers, which is 1,311 AU. Its event horizon diameter 393.4 billion kilometers, which is 2,622 AU. The Kuiper Belt, the ring of icy bodies that includes Pluto, extends to about 50 AU from the Sun. Ton 6/18's event horizon diameter is 52 times larger than that. The heliosphere, the bubble of solar influence where the Sun's magnetic field meets interstellar space, extends to roughly 100 to 120 AU. Ton 6/18's event horizon diameter is more than 26 times the diameter of our Sun's entire sphere of magnetic influence. Voyager 1, at roughly 163 AU from Earth, would be 6% of the way across the diameter of Ton 6/18's event horizon. The speed of light is 299,792 kilometers per second. A photon crosses the diameter of Earth in 42 milliseconds. Sunlight reaches us in 8 minutes, and somewhere in the universe tonight, there is an object whose gravity is strong enough to pull that light backward. That object is a black hole, and this video is going to show you exactly what it is. In numbers, in physics, in comparisons you can actually feel, with a level of depth that most explanations never reach. Here's what we're covering: how black holes form from the deaths of massive stars, the 4 distinct types from city-sized to solar system-sized, the true scale of each, built comparison by comparison until the numbers actually land, the event horizon and what it really is, geometrically, which is stranger than most descriptions let on, what happens physically when you approach one, and how radically different that experience is depending on which type, what gravity does to time near a black hole, with real measured examples from current technology, what happens to matter that falls in, what black holes actually look like when we point our best telescopes at them, how they slowly die over timescales that make the current age of the universe look like a warm-up, the first photographs ever taken of a black hole's shadow, how many of these objects exist in the universe, the deepest open problem in theoretical physics that black holes expose, what gravitational waves have taught us about them, and what all of this, taken together, tells us about the structure of reality. This is going to take a while, and that's intentional. Before we start, if you found this channel tonight, subscribe now. We build long-form space documentaries designed for people who want to actually understand something by the end of a video. And drop a comment right now. Where in the world are you watching from? And what time is it? I read every single one. Someone watched last week's video from a research station in Greenland at 2 a.m. on a Sunday. Someone else sent a comment from a train platform in Seoul during their morning commute. Someone in São Paulo watched the entire previous upload while working an overnight shift. Tell me where you are. I want the picture. All right, let's slowly ease into this. A black hole is a region of space-time where the escape velocity exceeds the speed of light. That sentence contains the entire concept. Escape velocity is the minimum speed required to leave the gravitational pull of an object without any additional thrust. From Earth's surface, it's 11.2 kilometers per second. From the surface of the Sun, it's 618 kilometers per second. The fastest spacecraft humanity has ever launched reached about 70 kilometers per second. From the edge of a black hole, the escape velocity is 299,792 kilometers per second, the speed of light itself. Since light speed is the absolute maximum at which anything in the universe can travel, nothing gets out. Mass creates gravity. Compress enough mass into a small enough space, and the escape velocity crosses that threshold. For a mass equal to our Sun, 2 1030 kilograms, this happens at a radius of about 3 kilometers. A sphere 3 kilometers in radius, containing all 2 octillion kilograms of the sun, would be a black hole. This seems like an engineering problem. Take a sun, squeeze it. But in reality, no force we know of can squeeze a star to that density, except gravity itself. Under the specific conditions that occur when a massive star exhausts its nuclear fuel and collapses. The boundary at which escape velocity equals the speed of light has a name, the Schwarzschild radius, named after Karl Schwarzschild, who derived its mathematical expression from Einstein's equations of general relativity in 1916, while serving in the German army on the Eastern Front. A year after Einstein published the theory, Schwarzschild mailed his derivation to Einstein from the trenches and died of disease a few months later, never knowing what he'd found. The Schwarzschild radius for any mass m is, or R2gm c2g, is the gravitational constant. C is the speed of light. M is the mass. Plug in the sun's mass and you get roughly 2.95 kilometers. The radius of Earth gives you 9 millimeters. The entire mass of Earth, compressed to a sphere the size of a large marble, a black hole. In the universe, no process actually compresses Earth mass objects to black holes. The objects that do become black holes are far more massive, and they get there through a specific pathway that we'll go through in detail in the next section. But the key thing to take from this part: a black hole is defined by a single geometric boundary, the event horizon, at the Schwarzschild radius. Inside it, escape velocity exceeds light speed. Outside it, extreme gravity, but physics still works normally, and escape is still possible if you accelerate hard enough. The event horizon itself is the dividing line. It's purely geometric, not a physical surface, not a wall of any kind. A mathematical threshold written into the curvature of space-time. What happens at that threshold and what lies beyond it is what the rest of this video is about. Stars maintain their size through a balance between two forces acting on their entire volume simultaneously. Gravity, pulling every particle of the star toward the center. Radiation pressure, the outward push of energy released by nuclear fusion in the core. These two forces are in equilibrium during a star's main sequence lifetime, precisely balanced across billions of years, holding the star at a stable diameter. For a star like our Sun, this equilibrium holds for about 10 billion years total. The Sun is 4.6 billion years old, comfortably in its middle age. For a massive star, one born with 25 or more times the Sun's mass, the equilibrium is far less stable, and it ends far sooner. A 25 solar mass star may exhaust its hydrogen in only 6 million years. The more massive the star, the faster it burns. A 100 solar mass star might last only 3 million years. For context, 6 million years ago, our ancestors were bipedal apes in Africa. The most massive stars live and die before our lineage had learned to walk upright. When the hydrogen runs out, the core contracts and heats until helium fusion ignites, then carbon, then neon, oxygen, silicon, each stage shorter than the last, each requiring higher temperatures and pressures than the one before. The silicon burning phase lasts roughly a week. At the end of it, the core is composed almost entirely of iron and nickel. Iron is where the process terminates. Every fusion stage up to iron releases energy. Lighter nuclei combine into heavier ones, and the mass difference is converted to energy via EMC2. But iron and nickel have the most tightly bound nuclei of all elements. Fusing iron into anything heavier absorbs energy rather than releasing it. With the energy source cut off, radiation pressure vanishes. Gravity, now unopposed, accelerates the core's collapse. What follows takes 0.25 seconds. The iron core, approximately 1.4 solar masses, roughly the size of Earth, collapses to a sphere 20 to 30 kilometers across in a quarter of a second. This compressed object achieves nuclear density, the same density as the nucleus of an atom, roughly 4 × 10 or 17 kilograms per cubic meter. A teaspoon of this material would weigh about 2 billion tons. When the core reaches nuclear density, a quantum mechanical pressure called neutron degeneracy pressure, the same pressure that prevents neutrons from occupying the same quantum state, halts the collapse temporarily. The infalling outer layers of the star, still in free fall at a significant fraction of the speed of light, slam into this suddenly rigid core and bounce. The resulting shock wave, energized by a flood of 1058 neutrinos streaming outward from the collapsed core, tears the outer star apart. A core collapse supernova. Total energy released, approximately 3x 1046 joules. To give that a reference, the Sun will emit approximately 1044 joules of energy over its entire 10 billion-year main sequence lifetime. A supernova releases 300 times that in a few seconds. In the visible light alone, a fraction of the total, a supernova can briefly outshine its entire host galaxy of hundreds of billions of stars. In gamma rays and neutrinos, the numbers dwarf visible light entirely. At the center of the expanding remnant, one of two things remains. For progenitor stars up to roughly 20 to 25 solar masses, neutron degeneracy pressure is sufficient to stabilize the collapsed core. What's left is a neutron star, 20 kilometers in diameter, 1 to 2.5 solar masses spinning rapidly, sometimes detectable as a pulsar from its beams of radio emission. For progenitor stars above that mass threshold, and the exact cutoff depends on the star's chemical composition, rotation rate, and other factors, the core mass exceeds what neutron degeneracy can support. The collapse continues through nuclear density, through any scale at which known physics can apply, and the curvature of space-time closes off completely. A black hole forms, in the fraction of a second following core collapse. In the most energetic explosion known to astronomy, the black hole announces its presence with silence. No light escapes it from the moment of formation. The supernova remnant expands outward, carrying the star's processed elements, carbon, oxygen, iron, and elements heavier than iron synthesized in the explosion, into the surrounding space. These elements will eventually be incorporated into new molecular clouds, new star-forming regions, new stars and planets. The iron in your blood, the calcium in your bones, the oxygen in the air around you right now, forged in stellar cores and stellar explosions, scattered into space, eventually gravitationally collected into the solar system, then into the Earth, then into life.